There are three kinds of integrals that arise in vector calculus: line, surface, and volume. A line integral takes a vector field v and integrates it over some curve. The prototypical example of this in physics is the work. When a particle moves through some force field, F, the work on that particle is the line integral of F dot dr. A surface integral involves a vector field v integrated over a surface. The main example of this in physics is the flux, like the electric flux that appears in Gauss's law. And finally, a volume integral is the integral of a scalar, or sometimes a vector, over some region of three-dimensional space. A good example to think about here is the mass. If you have an object and it has some density, rho of xyz, and you integrate that density over the region of the object, you will get the total mass. In this video, I'm going to discuss the three types of integrals, and for each one, I'm going to define it, I'm going to tell you what it means, and I'm going to do some examples of computing it. Let's start with line integrals. The line integral of a vector field v over some curve is written as integral v dot dr. Let me first tell you exactly what this means. The easiest way to do it is to think about a parametrization for the curve. If we specify our curve as x of lambda, y of lambda, and z of lambda, i.e. we give its Cartesian position x, y, and z as a function of some parameter lambda, then we can group these into vector r of lambda. Now consider the derivative dr d lambda. This is a tangent vector to the curve. If we dot this derivative into the vector field v that we're trying to integrate over the curve, then we get a scalar, and we can just integrate that scalar d lambda. So this is what we mean by the line integral. It's the integral of dr d lambda dot v d lambda. Now notice that lambda could be anything. Doesn't matter what parameter I choose, this expression will take the same form and give the same answer. So that's why we usually don't write the two lambdas. If you like, you can think of them as having canceled, and we just write integral v dot dr. But this form is good for more than just a shorthand. It's very intuitive. It's actually telling us what's really happening when we do this line integral. To see this, imagine taking some curve in three-dimensional space and dividing it up by a bunch of straight lines. And we'll draw an arrow on each straight line, so it's a little vector pointing from one point on the curve to the next. As we increase the number of little straight segments, we get better and better approximations to the curve. Now, what is the line integral? Well, it says we're dotting the vector field v we're trying to integrate into these little segment arrows. You could think of these as some delta vector r that, as we make them smaller and smaller, will go over to d vector r in the usual way that the integral is defined using Riemann sums. And in fact, this is a totally valid alternative definition of the line integral using the Riemann sum. So, this way of thinking about it tells us a little better what's going on. The line integral is you divide up your curve into a bunch of little segments, you dot those segments with the vector field, and you add up the lengths. For computing line integrals, there are two ways to go. One is to parameterize your curve and just use this formula. Now it's just an ordinary integral, which you know how to do. But that's not always the most efficient way. Another good way to do it is to use this formula we had for d vector r in the derivatives video. dr is equal to dx x hat plus dy y hat plus dz z hat. If we plug that into the integral, now we see dx, dy, and dz. And if we have formulas that relate y, x, and z to each other, we can sometimes play around with them to get everything in terms of an integral with just one, say, dx. This is equivalent to using x as the parameter, but often it's a lot quicker than just going through this whole lambda rigmarole. I'll show you how this works with a few simple examples. We'll start with a two-dimensional example. Consider the vector field given by y squared x hat plus 2x y plus 1 y hat. And we'll integrate this vector field over a path in the two-dimensional plane, starting at the point A, given by 1, 1, and ending at the point B, given by 2, 2. Now for a line integral, I have to tell you not just the start and the end, but also the full path between them. And let's start with a straight line. So we'll call this path 1. And this straight line from A to B, if we extended it, it would go through the origin. And it has slope 1, so path 1 is just the line y equals x. And the other thing we're going to need to know is how little displacements along the path are described. And the trick to getting that is just to take d of both sides of the equation and write dy equals dx. Now, let's consider the line integral of v dot dr over path 1. Remember, dr is just dx x hat plus dy y hat. In 3 dimensions, we'd also have dz z hat. Now, we get to evaluate both v and dr on path 1. So this line integral, we can write as integral of 1 of v, evaluated on path 1, meaning we get to use y equals x. So v just becomes x squared, x hat, plus 2x x plus 1 y hat. This thing here is v with y equals x. That gets dotted into dr, but dr is also evaluated on the path 1, and we get to use dy equals dx. So we write dr as dx x hat plus dx y hat. Notice that I don't set x equals y under the hat or anything like that. X hat and y hat are just the universal fixed basis vectors for the two-dimensional plane. So this here is the infinitesimal displacement with dy equals dx, which we're allowed to do on path 1. So now we just do the dot product, and we get x squared dx from the two x components, plus 2x x plus 1 dx from the two y components. And now we finally have just an ordinary integral over x, which I can simplify. Here's a 2x squared, there's an x squared, so I have 3 total x squareds, and then I also have 2x dx. Now, I stopped writing path 1 at this point because it became just an ordinary integral over x, so we can be more specific. On path 1, x starts at 1 and ends at 2. So the limits of integration are from 1 to 2. So now we just do this integral, that's x cubed plus x squared from 1 to 2, which is 2 cubed plus 1 plus 2 squared minus 1 cubed plus 1 squared. And this is 8 plus 4 minus 2, which is equal to 10. So the integral over path 1 of v dot dr is 10. Now, the line integral can depend on the path. So let's consider another path where we go out to the right, then we make a right-hand turn, and we go up. So that path is going to be called path 2. Of course, I could draw any squiggle I want, but then it might be hard to find a simple mathematical formula for the example. So for path 2, it's going to be difficult to describe it with a single equation like y equals x. Because over on the first leg, it's at constant y equals 1, and over on the second leg, it's at constant x equals 2. So for a path like this, it's going to be convenient to split it into 2. So let's say path 2, 1, the first part, That's described by, well, it just sits at y equals 1. So we'll say y equals 1, and then dy equals 0. And then for path 2, 2, the second part, we will have, now we sit at x equals 2. And so dx equals 0. And now we just do the same thing. The integral of v dot dr on path 2 is, we look at v, but we get to use y equals 1. And so v becomes just x hat plus 4x, y equals 1. 1 plus 1 is 2, times 2 is 4. All times y hat, that is v with y equals 1. And now dr, written over here, we get to use dy equals 0, so this term goes away. It's just dx x hat. This is dr with dy equals 0. Now this was just the first path, so that was part 1 of path 2. So we need to add to that another integral where now we do path 2. So this is 1. This is 2. So now on this second part, x is 2. So v becomes just y squared x hat plus 4 y plus 1 y hat. That is v with x equals 2. And then dr, we get to set dx equals 0. So this just becomes dy y hat. This is dr with dx equals 0. So we've got those two things. Now we do these dot products. This is a simple dot product, only the x components matter. The first term there is just integral dx. And in this dot product, we only get the second term. So we get integral 4 y plus 1 dy. Now they're just ordinary integrals. This one is an integral over dx, and x ranges from 1 to 2 over that path. And y over the second path ranges from 1 to 2 as well. So we just have to do these integrals. The integral from 1 to 2 dx is just the length of the region. That's 1. And the integral of this function, we can do it with the antiderivative, so it's going to be 2y squared plus 4y, all evaluated from 1 to 2, which is equal to 1 plus 2 times 2 is 4. Sorry, 2 times 2 squared is 8. Plus 4 times 2 is 8. Minus 2 times 1 is 2. Plus 4 times 1 is 4. So it's 16 minus 6, so this whole thing is 10. And the answer is 11. So the integral over path 2 of v dot dr equals 11. So that's a simple example that shows you kind of how to compute. The strategy is basically to describe each path with some formula relating the variables to each other, take d of that formula, and then plug everything into v dot dr and just play around until it looks like ordinary integrals. Now let's do an example where we're going to use a parametrized curve to compute the line integral. Let's make our vector field y x hat minus x y hat. And let's make our curve 3/4 of a circle. So we'll start at x equals 1, y equals 0. We'll go out in a circle. but we'll stop here on the negative y-axis. So that's our curve. That's supposed to be a circle. Now, if you start doing it the way I described in the previous example, you would want to realize that we can describe the circle as x squared plus y squared equals 1. And then you could write y equals square root of 1 minus x squared. But that would only get you the top half. That's where y is positive. You really need 2 branches, plus or minus. And you could do this and you'd have a lot of square roots and you'd have the curve split in 2. And eventually you'd get the right answer. But there's a more efficient way, which is instead to use a parametrized curve. So let's parameterize this curve. Let's remember that a circle can be written in terms of sines and cosines. We have x of some parameter lambda is just cosine lambda, and we have y of some parameter lambda is just sine lambda. This is in some cases how the cosine and sine functions are actually defined. So now we can get that, and we have also that now dx is, well, the derivative of cosine is minus sine lambda d lambda, and dy is cos lambda d lambda. And now we do the same sort of thing as we did in the previous video. We get to use these expressions in both v and dr. So v is yx hat minus xy hat. We plug in. V becomes sine lambda x hat minus, and then x is cosine lambda y hat. And remember, dr is always dx x hat plus dy y hat. So with dr, we have dx is minus sine lambda d lambda. And dy is cosine lambda d lambda. Now we do this dot product, and we will find that it is minus sine squared lambda from the first term, minus cosine squared lambda from the second term. Both had d lambdas. And of course, sine squared plus cosine squared is 1, so this is just minus the integral of d lambda. So we have a very simple integral. We didn't have to mess with any square roots or anything like that. And we just have to figure out what lambda does along this curve. So lambda starts here at 0, so that y equals sine lambda equals sine 0 equals 0, as we're supposed to be. And then lambda is really just the angle around this curve. So over here, it's just 3 pi over 2. So this is actually the integral from 0 to 3 pi over 2, which is just equal to minus 3 pi over 2. And so that's the integral of v dot dr. Now we did this by the notational trick of writing dr this way, but if you really prefer to just think of your fundamental definition of a line integral as a parametrized curve, i.e., if you like the viewpoint that this thing is really defined to be the integral of dr d lambda dot v d lambda, then that's what we've done here. This here is r of lambda, x of lambda x hat plus y of lambda y hat. And by doing these manipulations, we've just plugged into this formula and done the ordinary integral. Now we come to surface integrals. A surface integral involves a vector field v integrated over some two-dimensional surface in three-dimensional space. When I introduced line integrals, I first gave a parametrized definition, a definition involving a curve that was parametrized, and then I discussed a more intuitive way of thinking about it, which was also an alternative definition. In the surface integral case, I could do the same thing with a parametrized surface, but the mathematics of parametrized surfaces is generally somewhat unfamiliar. So I'm just going to skip to the second definition, which is a little more intuitive. The surface integral is written as the integral of v dot dA. Think of dA as a little patch of surface with area equal to the magnitude of dA, and with direction equal to the normal vector, the vector that is orthogonal to the surface. So when we compute v dot dA, what we're computing is the flux through that surface, the magnitude of v times the area of the surface, the magnitude of dA, times the cosine of the angle between them. So we're adding up the flux of all these little surfaces over the whole surface. And that's why we call the surface integral the flux. So when you compute surface integrals, you have to figure out what this little dA is. And there's no foolproof way of doing that. So the best way to illustrate it is just to do some examples. For an example of a surface integral, let's consider the vector field v equals y squared x hat plus 2xy plus z squared y hat plus 2yz z hat. And let's integrate this vector field over the surface of a cube. So we'll put our cube with one vertex at the origin, and we'll just have it length 1 on all sides. So if you like, it's the unit cube. Now, we have to make sense of this expression integral v dot dA. Whenever your surface has edges in it, it's going to be useful to divide it up into subsurfaces. So this cube has 6 faces. So the integral over the cube can be written as the integral over the top of v dot dA plus the integral over the right side of v dot dA plus the other 4 faces. Let's start with the top. On the top, the z-coordinate is constant. The z-axis here shows us in this picture that the top of the cube is described by z equals 1. The x and y coordinates change over the top, so I'm going to write x and y are free. They vary between 0 and 1. This means that our area element on the top is going to involve dx and dy. Now in general there might be a function of x and y in front, but the top here is just a square described by Cartesian coordinates, so the area of a little patch is just dx times dy. And then the direction is the normal vector, unit normal vector n hat, which in this case is just z hat. So we just plug in. What is v on the top? Well, we get to use z equals 1. So v is y squared x hat plus 2xy plus 1 squared y hat plus 2y times 1 z hat. That's the vector field v restricted to the top, so I get to use z equals 1. And that gets dotted with dx, dy, z hat, the area element on that face. So when we do the dot product, just the last term contributes, and we end up with the integral of 2y dx dy. This is the integral over the top face, but now it's just an ordinary double integral over x and y, which are our coordinates on the top face. And so we can just do it by inserting the ranges of x and y, which on this face are 0 to 1. So this integral is just 1. This integral is, the antiderivative is y squared, so again it's just 1. And so the answer for the top face is just 1. Let's move on to the right face. On the right face, we have not z equals constant. The right face is at constant y. It's described by y equals 1. And the other 2 coordinates, x and z, are free. They change on this right face. So our area element is going to involve dx dz. And again, it's just going to be dx times dz because these are just Cartesian coordinates. The area of this little thing is the product of the lengths of the sides, and the lengths are dx and dz. But the normal vector here is now in the y direction. So y hat. So the area element on the right face is dx dz y hat. Now we do the same thing. We plug in for v using y equals 1, and we get x hat plus 2x plus z squared y hat plus 2z z hat. And then the area element is dx dz y hat. We do the dot product, only this middle term contributes. We find the integral to x plus z squared dx dz. And now we just have an ordinary double integral over x and z, and so we just go ahead and do it. We insert the ranges of x and z. In this case, again, it's just 0 to 1 for each of them. So we have integral 0, 1 dx, integral 0, 1 dz, 2x plus z squared. And I won't do the integral in front of you, but it comes out to 4/3. Then you can keep going. For each face, you find a separate description of the coordinates on the face, an area element for that face. You get all the answers, you add them up, and a good exercise is you can check yourself after you've gone through this. The total that you get should be 2. Now, if your surface is more complicated, it can take a bit of ingenuity to figure out what dA is. But again, you can always go back to the definition that the magnitude is the area of a little patch, and the direction is normal to the surface. So for example, suppose we considered as our surface a tilted plane. Not just the xy plane, but one that's raised a little bit, like so. And let's call the angle of tilt theta. So this tilted plane is described by z equals the rise over the run, which is tangent of theta, times y. I put x here, y there, and z there. Now, what is the area element? Well, let's draw a little picture. We imagine changing x a little bit, changing y a little bit, and we want to know the area of this patch. So what is the area on the plane when we change x and y? And what I mean is by dx and dy. So if we're going to use x and y as our coordinates in this way, our area element needs to feature dx and dy. But it's no longer just equal to dx times dy because this plane is slanted. Dx times dy would be the area of a little square sitting down here at z equals 0. But the area of the rectangle that corresponds to changing x and y a little bit is not the same. So to see what's going on, let's imagine zooming in here, and let's look at it edge on. So it looks something like this. We're not going to worry about the x direction because everything is symmetric in that. But this is our little bit dy. But now look what happens. There's also a raise dz, such that the actual distance here, ds, is not equal to dy. Instead, there's a factor of cosine in there. ds is equal to dy over cosine of theta. So the area element is equal to ds, the actual distance on the plane, times dx, the other distance, And then by this formula, that's actually dx dy over cosine theta. So I need this cosine theta here as I try to figure out what the area element is. Now I need to do the direction. Well, the vector is supposed to be normal to the plane. Let's look in our diagram here. Here's the surface of the plane. Let's write the normal vector like that. So we can resolve it into its components again, and we find that the normal vector is just equal to cosine theta times the vertical direction z plus sine theta times the horizontal direction y, but I actually need it to go to the left here, not to the right, when theta is positive, so this ought to be a minus sign. Okay, so those are my two components of the area element. So d vector A is going to be equal to its magnitude times its direction, cosine theta z hat minus sine theta y hat. And now I'll just cancel the theta, so I'll have dx dy z hat minus tan theta y hat. So let's see if this makes sense. At theta equals 0, tangent goes away. That's when the plane is just flat, and we get back just dx dy z hat with the normal vector vertically. And as theta goes to 90 degrees, well, this term is blowing up, so the direction is approaching y hat, which is what we minus y hat, which is what we expect because the normal vector should tip over and point left. And the reason it's blowing up is because if this plane is very vertical, when you change y a little bit, you actually introduce a big area on the plane. And so it does make sense. So that is the area vector, area element vector. And if we were to do a surface integral, we would just plug this in the usual way. Now, when we do surface integrals in general, usually we try to find a good coordinate system. This is a bit of work. So for the more common ones, we have special coordinate systems. For example, if we're doing a surface integral over a sphere, well, the normal vector would just be r hat, the unit vector of spherical coordinates. And it would be natural to describe the sphere in terms of theta and phi, polar coordinates on the sphere, and a little area element here would be given not by d theta, d phi, but with this usual sine theta correction factor, since the latitude lines get smaller and smaller as theta approaches 0. So if you have a surface integral involving the sphere, you'll want to use curvilinear coordinates, spherical curvilinear coordinates, and the area element will just be sine theta, d phi, r hat for this unit sphere. So usually the key to finding the area element is making a good choice of coordinates. Now we come to volume integrals. A volume integral is an integral of some scalar field, f, over some volume, some region of three-dimensional space. This little d tau is to be thought of as a little chunk of three-dimensional space, much like dA in a surface integral was a little patch of the two-dimensional surface, and dr in the line integral was a little bit of the one-dimensional curve. So d tau is just dx dy dz in Cartesian coordinates, and then the volume integral becomes an ordinary triple integral. For this reason, volume integrals are generally a little easier to handle than line and surface integrals. Let's do a quick example of a volume integral. If your volume has a nice description in Cartesian coordinates, like a cube, then you should just use d tau equals dx dy dz, and this just becomes an ordinary triple integral. But what if your volume isn't so nice in Cartesian coordinates? What if, for example, it's a sphere? Well, for a sphere, we want to use spherical coordinates. And to figure out what d tau is in spherical coordinates, You can look up the definition and use the general Jacobian matrix formula. You can figure it out just by drawing little pictures, thinking of little chunks where r, theta, and phi change a little bit, and ask what volume of space is subtended. Or you can just remember the formula. In this case, it's r squared sine theta dr d theta d phi. So for example, if we wanted to compute the volume of a sphere, that would just be the volume integral of 1, rather just d tau. And so that's the integral over the sphere of r squared sine theta dr d theta d phi. And now again, we just have a triple integral. So we have the integral from 0 to 2 pi of d phi. We have the integral from 0 to pi of sine theta d theta. And we have the integral from 0 to capital R, if that's the radius of our sphere, of r squared dr. This integral is just 2 pi. This integral is minus cosine theta from 0 to pi, which is just equal to 1 plus 1, which is 2. And this integral is just r cubed over 3 from 0 to capital R, which is equal to capital R cubed over 3. So put it all together, 2 pi times 2 times a third r squared is 4 pi over 3 r cubed, and that is the volume of a sphere. Finally, I need to discuss a very important and also very annoying concept called orientation. When I discussed line integrals, I said that the line integral was an integral of a vector field along a curve. But the curve is actually not quite enough information. I also have to tell you which way to move along the curve. I drew all those little arrows, but if I had reversed the direction of those tangent vectors, I would have gotten the same answer except with a minus sign. So there's a sign ambiguity in the line integral if I only tell you the curve. Therefore, the line integral should most properly be thought of as an integral over an oriented curve. Surface integrals, there's a similar story. There's an area element, dA, that appears in the surface integral, and I defined that by talking about the normal vector to the surface. But which normal vector? There are two choices. For example, for a sphere, I could pick the outward pointing normal vector or the inward pointing normal vector. Again, the ambiguity is just an overall sign, but you do have to keep track of it. And so most properly, we think of a surface integral as an integral over an oriented surface. By the way, not every surface even has an orientation. If you can't find a continuous choice of normal vector, then you say the surface is not orientable and you can't even do a surface integral. You can Google the Mobius strip if you want to learn more about that. So this orientation is just a choice of sign, and you might think it's pretty trivial. You might think it's just always given to you as part of the problem, right? If you're computing the flux through some surface, say representing the flow of water or something, you have to say which way through the surface you're considering the flux, right? It's a kind of trivial thing. It's just a sign. Why do I care so much? Well, I care because there's a beautiful, amazing, important, let's say essential theorem called Stokes' theorem, which involves the orientation in a key way. Stokes' theorem is the generalization of the fundamental theorem of calculus, and there's a version for each of the 3 kinds of integrals and correspondingly the 3 kinds of derivatives. So in the next video, I'll tell you all about Stokes' theorem.